we have the Professor Andrea Matta for giving a nice talk. So first of all, let me introduce Professor Matta. Andrea Matta is a full professor of manufacturing and production systems at the Department of Mechanical Engineering of Politecnico di Milano. He graduated in industry engineering at Politecnico di Milano, where he develops his teaching and research activities since 1998. He was a distinguished professor at the School of Mechanical Engineering of Shanghai Jiao Tong University from 2014 to 2016, and a guest professor between 2017 to 2019. He has been visiting professor at École Centrale Paris, France, University of California at Berkeley, USA, and Tongji University, China. He is a scientific response of the research area design and management of manufacturing systems at MUSP. Is a laboratory for the research area design and machine tools and production systems. His research area includes analysis, design, and management of manufacturing and healthcare systems. He has published over 170 scientific papers on international and national journals conference proceedings, very productive. He is the editor-in-chief of Flexible Services and Manufacturing Journal since 2017. So past member of editorial board of OR Spectrum Journal and IEEE Robotics and Automation Letters Journal. He is a chair of the technical committee IEE RAS Sustainable Production Automation. He is a member of a scientific committee in several international conferences, member of the steering committee of PhD on mechanical engineering, member of the ADA University Advisory Board. According to his significant contribution, Professor Matta was awarded with the Shanghai 1000 Talent and Eastern Scholar in 2013. So today we have the great honor to invite Professor Matta to give a talk. So he will give a talk on the topic of data-driven creation and operation of digital twins for discrete event systems. And thank you so much, Professor Matta.
Thank you for this nice introduction that creates great expectations. So let me, some technical stuff, I will share the screen. I can share the
please.
Screen now. Sure. Yes, perfect. Can you see, I guess, right?
Yes, it's working perfectly.
Perfect. So again, thank you. Thank you for inviting me. As I said, I always have a plan to go to Hong Kong, and so I'm missing again this opportunity, but let's plan for the future, by sure. So let's focus on the talk, but before starting the talk, just a brief history of a little bit of myself, at least from the scientific point of view. Today I will talk about digital twins of discrete event systems, even if in my applications I will focus mainly on manufacturing systems. Okay, why? Because I'm in mechanical engineering, I'm in industrial engineering, but in the department of mechanical engineering in the manufacturing systems lab. And so manufacturing has been my main field. My second field has been healthcare, mainly home care logistics. But I started working on, I was a queuing guy. Okay, so a Markovian guy, queuing guys, and so on. So for many years, I developed analytical methods for performance evaluation. And then as I always, I used to say, one day I moved to the dark side. Okay, so I moved to simulation. And so I started to develop all my research activities using simulation models. And finally, in the last years, what let's say my focus is not on simulation or is on queuing, but I'm working on models that integrate both. Okay, so I think now it's old-fashioned to say I use only simulation, I use only queuing, but we use models, different models that I can integrate in multi-fidelity models, and in order to analyze better a system. Okay, but this is my trajectory. Okay, and so finally, yeah, working on simulation, I come out with digital twin, following, let's say, the wave of Industry 4.0. So now this talk will be focused on digital twins, so of discrete event systems, and mainly on what I call operation of digital twins. Okay, so these digital twins should be operative day by day, shift by shift, hour by hour, depending on the application. So my lab is working on models and methods to make this digital twin operationally efficient and effectiveness. So this is the agenda of my talk. I will first give an introduction on digital twins. I will avoid, let's say, very common concepts. Okay, I will try to say something that came from our analysis. After this introduction, I will focus on, let me use the laser pointer. Yes, I will focus on three main research problems my team is working, that these belong to the what I call operation of the digital twin. So how to generate a digital twin, how to validate a digital twin, and how to synchronize a digital twin with the physical system. The first area, automated generation of digital twins, is more developed. We are starting on the other two, and then I will conclude. I would say that if there are questions, you don't have to wait until the end of the talk, but you can interrupt me and ask questions. Okay, so digital twins are, let's say, are becoming very relevant in the industry, also in terms of business value. We see here some main figures, like that the market size of the digital twin is expected to be more than 60 billion euros in a few years, by 2027. Okay, with a very high growth of market share. You see the CAGR index that it is expected to be more than 40% in the period 21-27. So they are important, they are becoming more important, and it has a value. So this means that there are companies that are investing. Where they are investing? Surely manufacturing. You said that manufacturing is representing the biggest sector for digital twin deployment. More or less 1/3 of the total spent or the total investment last year. You see here this figure. Manufacturing is more or less 1/3, and then you have energy and utilities, and then all the other sectors. And North America until now is spending more, okay, in the manufacturing. You see here 67%. And the expectation by Gartner is that by last year, okay, this is already updated, but the top 2,000 companies will use a digital twin to improve their processes, and they are expecting gains up to 25%. These are very significant numbers. So just to conclude, all the forecasting companies are expecting digital twins to be important and play a very relevant role industrially. What I mean for digital twins, I mean a system here, I call a manufacturing system, but it can be a warehouse system, it can be a transportation system. I have sensors, so all the system is sensorized. I get data from these sensors, and then I generate a model, okay? A model that my digital twin will use. And then this model that for my purposes is a simulation model. Can be used for different services. For instance, you can use for scheduling the manufacturing job shop. And when you schedule, maybe you schedule when you have a, I don't know, a resource that is a machine or a line that is failed, cannot work. So you are forced to change your schedule plan. So you have a trigger event here that is asking for a new scheduling plan that will be generated using the simulation model of the digital twin. And then the new plan will be prescribed and implemented here. Okay. So you see that if we call, so the digital twin, so the digital part that is using the simulation models and also generating a new plan, so providing a scheduling service, then you see that we have an interaction between digital twin and physical system. So we have from physical system to the digital and from the digital to the physical. And then it may happen that during the time, something happens to the system because the system is not static. A production system will have a life of at least 15 years, 20 years, why not? Okay. So after the setup of the production system, it's very frequent that changes occur in the machines, in the robots, in the allocation of the jobs, the product mix is changing. And so someday the physical system will change. And so we are forced to change the model used by the digital twin. So this is what I call model update. So you see we have a first loop of models of the digital twins from the generation to update. That has to be always followed, not in the beginning of the digital twin or the physical system, but always in the whole life of the physical system. And then we have the operational, more operational part from data gathering to the prescription. This is another one. We did a recent literature analysis on digital twins, where digital twins, I'm saying, it's not an offline simulation for me. We have, so the loop, these loops that I just described. So we did this literature analysis, and we were interested to, we selected all the papers in which there was a proof that the digital twin was related to a real project. So there was a real implementation. Okay. So starting from more than 500 papers, we arrived to 21 papers. So we found only 21 papers in which we have a significant evidence that the authors implemented a right to a real digital twin. It's not a standard simulation like 20 years ago. Okay. So very few papers. So this outline that digital twins are still in the early period. So I think the better will come. And you see here, so these are the criteria of our research. The main applications of digital twins that we found, maybe because we were biased in our research, but obviously we searched in manufacturing and production. It was a dynamic schedule. And then you have several other applications. And if you see we also judged the level of the implementation using the technological readiness level. And you see the TRL. The TRL of these papers, from our opinion, arrived until 7. So still we don't have any evidence until of a full implementation until 9. We are using the town model, so the 5-dimensional model for the digital twin, in which we have a physical part, a virtual part, the services provided by the digital twin, the data that are central in the model, and the connections. So we are adopting this model that we have seen is quite convenient. And here you see some examples for each component of the 5-dimensional model, where I listed some examples. For instance, the physical entity can be a manufacturing system, warehouse, a supply network, and so on. The virtual entity, in my view, the digital twin will not only use one model, but I see a digital twin as a portfolio of models. And depending on the decision you have to take, then you will use one model or another model, or more than one model. So for instance, you can have a data model. For instance, if you want to predict, I don't know, a number, the production, you can, if you use the sample average formula that is very simple, this can be a digital twin. It's a prediction model. Okay, very, very rough. Okay, but it's a model. We can have an analytical model. We can have a queuing model used by the digital twin, or we can have more complicated models like a simulation model, discrete event simulation to support the scheduling, or we can have also physical models like here. I'm simulating the stress on this part of the time machine. And obviously, I can also build a surrogate model from all this. Okay, so I see the digital twin using a variety of models depending on the purpose. And then these are the services that the digital twin will provide, from prediction, scheduling, sequencing, optimization, control. Obviously, these are the services that might provide. And then we have the data model. Obviously, we can put the data in standard databases or in clouds, but since we are collecting a lot of data on a temporal way, so these are time series. So time series databases will become more important. And then for the connections, obviously, we have the standards of the IoT technologies, so MQTT, OPC, and so on. These are the standards that we are using. This is in our view are the features that a digital twin must have at the left side. Without this, in my view, okay, we cannot call a digital twin. At the right side, something that is nice to have. But for instance, I cannot think at a digital twin if we don't have a bidirectional information flow from physical to digital and vice versa. If I cannot synchronize both digital and physical, digital twin cannot play anything. Since it is synchronized, the digital twin should have at least a monitoring service. That is really the basics. And then, since the physical system is not a dead system, it's a live system. It's changing every week, every month, even in the production policies, the transportation policies, then the digital twin should be adaptable. Because I cannot believe that there will be technicians changing the digital twin offline coding week by week, month by month. So because it will be too expensive, both in terms of money, but also of skills, because it's not easy to find skills to change the digital twin models. So I think that to be successful, digital twin should have an adaptation capability. And then the advanced features are the prediction capabilities, the optimization, and the capability to choose the models necessary for doing the analysis. And this is, from my point of view, is the evolution of what we call simulation, starting from 70s to digital twin. This is a standard. I think this is the evolution that followed. So when simulation started, the interaction with the physical system was offline and only from physical to digital, used for design purposes and offline analysis for standard problems like assembly line balancing, layout optimization, resource allocation in general. And then, starting from 90s, easier to connect with the data. And then let's say the model, the simulation model, started to be used online, okay? But the interaction was only from physical to digital. So this is what I call a digital shadow. Okay, something that is following like a shadow of the physical system, but it's not recommending, it's not prescribing anything. Used for monitoring, scenario evaluation, prediction, for scheduling, due date quotation, and so on. And then, after we are able to close this loop, then we have a bidirectional flow, so online application, and then I can use to make optimal decisions, optimal control, optimal coordination online. And this is what I call digital twin. Can be used for scheduling, online dispatching, maintenance planning, and so on. This concept, if you see here, this concept, now we call digital twin, but it's not. So the concept is not new. I think it's important to deserve to Jerry Banks from simulation field and this Mani Vanden, the first concept of what they call the real-time simulation, how to use simulation in real time to control a manufacturing cell. If you look at this paper, here you have a turning center, the concept is the same. So we cannot say that the digital twin is a new concept. All the technology is new. And at that time, was difficult to apply this. Now with the new technologies, it's much easier and cheaper. And then you have the same concepts from Kadar et al., Professor Monostori, but this is a real-time simulation concept. So why, okay, sorry. This is the architecture we are using in our digital twin deployment. So we have the real manufacturing system. We think there will be a manufacturing execution system to control the production cell or system. And then we have some required service for the operation of the digital twin, like synchronization, validation, and all the data stored. And then we have here the models. Now we are focusing only on discrete event simulation models, but as I said, we can have more. And this is the level of the provided services from performance evaluation, just a prediction, to optimization. Now let's focus on the services, the functions that the digital twin should have. So in my idea, we first have to generate the models of the digital twin, and this should be online because otherwise it's too expensive, and should be automated, or at least partially automated, because the generation of new models will be more and more frequent. After I generate a model, and then I should use for decision, but if the model is not valid, the decision will be wrong. So we need to validate the model. But if you look at all the validation techniques used in the simulation field, it is very difficult to apply in real time, online. So we need new models for online validation of digital twins. Also, and then I should use the digital twin And so we need synchronization, monitoring, and so on. And then sooner or later, I should update my model because the physical system changed some. So this is what I call operation of digital twin from generation to update. And we are focusing on this. Now, after this introduction, I will focus more on the first research topic, that is automated generation of digital twins. So it is more related to this part now, generation of the digital twin. So why we need an online and automated generation of digital twin? Assume that the physical system is this one below. We have three stations with the two part types, A and B, following station 1, 2, and 3. Okay, and I develop a digital twin that is a simulator here, corresponding to this system. This is in, I don't know, in month, now we are in May. Assume that in July, okay, something changed. I added a new station, station 4, and then I also changed the process plan of A and B. Now, this digital twin is not valid anymore. I cannot use for making decision, like a maintenance decision. And so I had to code. In my concept, the idea is to get the data from the physical system. You see this data. And then use this data to automatically generate the new digital twin that you see here. So we are working on automatic generation of discrete event simulation models, only using data. What does it mean to generate a simulation model? Here you see the layout of a physical system we work with, okay? It's a complex system. This is a simulation model in Arena code for those that know the Rockwell simulation software, okay? And you know, this is just, these are instructions that we code in a software. But behind the simulation code, we have a graph. We know by theory that every simulation model can have a graph representation. So I can say that developing a simulation model means theoretically to develop a graph. So if I want to generate a simulation model and I want to do automatically, this means to automatically generate a graph. This belongs to the research problem that is graph discovery or graph mining problem. So using the data, I want to mine the graph that is behind those data, explaining the data. Sorry, I come back here, that I collected from the station. So now we are able, using the data, to automatically mine the graph representing this manufacturing system. And then we converted the graph into a simulation code. Okay, how do we do this? We are doing using, using process mining approach. Okay, I think most of you knows data mining. Okay, process mining is used not to discover structure from I don't know, from a phase, but more phases that are composing a process. This process mining has three different branches: process discovery, conformance checking, it's a kind of validation, and enhancement, it's a kind of update of the model. Okay, so generation, validation, and update. Here you find the book of Professor van der Ast on process mining. This is just to show how process mining is becoming more and more important in the years. So the concept is this one. I get the data from the shop floor, I aggregate them, I have data logs, I use process mining, and then I discover my simulation. Process mining now is becoming very popular. You see, this is Simulate, a simulation software. Now simulate can accept as input file, a file coming from Disco, where Disco is a process mining software. So you see, we can even now, I can import a model that I discover in process mining using Disco, and I can import and simulate and simulate. But process mining, like in theory, in the basic algorithms, is very difficult to be applied for manufacturing systems, because manufacturing systems have some main special features that make process mining difficult to apply. These are the finite capacity resources. If you have a finite capacity, standard process mining has problems, because process mining was born to discover, let's say, service processes like banks, process flows without any limited capacity. It's difficult to control the aggregation level if you don't know what is manufacturing. It is high sensitive to wrong sequences or rare events. And then it is not related to performance estimation. It's just looking at the structure of the graph. Okay, so this is our literature analysis of papers related to manufacturing, and for instance, providing a framework. These are papers mining the production policy in the manufacturing system. These are papers mining the parameters of a production policies of a distribution and so on. So I start from the manufacturing system. I have 3 stations, you see. I put sensors, one here in station 1, another one after station 1. I have a conveyor bringing parts from 1 to 2. And then in station 2, still I have 2 sensors. And this is the pallet you see that move from station 2 and station 3. So from each station, in this example, for instance, I take 2 data logs, one for each sensor. So I have 6 data logs. This is my event log. This is an example of the event log. You see the part 2 crosses sensor 1 at this time, sensor 2 that is here at this time, and so on. So these are traces. And from these traces, I first generate or mine a graph like this, in which a graph is composed by nodes and arcs. And this is what is called model discovery, traditional process mining. This is nothing new, okay? I can use software that you find in the web. But then we developed model tuning algorithms that that simplifies this graph and is able to understand that these data logs belong to just one station. So I'm aggregating these 2 nodes, and I will only have 3 nodes, 1 for each station. So we are focusing here on model tuning. The rest is state of the art. Okay. So the tuning model is the method that is bringing from this complexity of graph by using standard process mining to something like this. Because this is very difficult to understand, this is quite easy, and also for simulation purposes. So what I'm putting in a tuning model? In a tuning model, I put the things that I want to emphasize. I like this picture from Professor van der Ast, in which this is a simplified map of the Eindhoven town, in which, for instance, I remove all the roads that are not important here, so abstraction. I aggregate parts of the city, I'm merging, okay? Like, for instance, in a production system, I can merge, I can aggregate stations in a certain area. I customize what I want to customize, and I emphasize, for instance, highways. I can emphasize some special processes. So the model tuning, I use this to navigate through the complexity of the graph, just discover, and to emphasize and aggregate what I think is important. That you think this is what we do when we build a simulation model. It is called the art of modeling, selecting the detail of level. So how can we do? Okay. We have to discover a graph. We have a graph, but from this graph, we have to select which nodes are important, which arcs are important, which ones can I remove or not. For instance, here, I can decide to aggregate these 3 nodes in just one cluster. The same here. I can think that this node is not important because maybe only once a part moved to this node. And why these are important, but I keep very detailed. How can I do this? I define, let me go here, sorry, first, an optimization problem in which the goal of the optimization problem is to decide the nodes and arcs of a graph. So discovering a simulation model means to discover a graph. So I solve an optimization problem to find the graph that maximizes the score function. What is the score function? This depends on the manufacturing system. But for instance, in our cases, we are seeing that it depends on the finite capacity of resources, on the routing of the parts, on the fact that we have contemporary events, so we can have batches, on recirculation of parts, and obviously we consider frequency. So more frequent paths are more important. So this will be a weighted sum of functions that I call a score function. So I decide nodes and arcs to maximize this function. And I can put constraints. These are very important because I can say that the maximum number of nodes will be limited superiorly, or also the maximum number of edges. What does it mean? It means that I can control the complexity of the simulation model. If this limit is very low, it means that I can say that 100 stations, I want to aggregate everything in 5 stations. This will means that simulation model will be very rough, but very fast to make quick and rough decisions. Or I can also decide to have a very detailed model. This is an example of some stations you see here, 6 stations plus a quality station here. And we see that if I put the constraint of only 2 nodes, the algorithm is aggregating from station 1 to 4 in just 1 node, and 5, 6, and quality station here in another node. This is just to have two machines in my simulation model, decoupled with buffers, but very simple model. Okay. If I change the constraint, I will have a more detailed model. We did several experiments. For instance, in the same machine, we put other sensors that are tracing the parts after very, very short time. Okay, so this happens a lot when you have a PLC that are, say, recording a lot of timestamps. But if the time between 2 different timestamps is very limited, it means that maybe this is not a process, a real manufacturing process. It's something in the same process. So our algorithm is aggregating also in this way. So 2, 1, 2, 2, and 2, 3 are aggregated here. And then obviously we have to discover the parameters and the distributions of the routing policies. Here we are using standard stuff like a kernel density estimation and just the frequency policies to estimate P1, P2, and P3 here. Okay, so what is the output? Can be just a simple graph, can be we are able to generate Pairwise model, or we are able to generate the event relationship graphs from data. Both Pairwise model and the ERG are formal models, so I can move from ERG to a Pairwise model. This is the same case study of 6 stations. After I calibrated my score function weights, you see I need to calibrate this, okay? And then if I choose to have only 4 stations, only 4 nodes, this is the production rate that I estimate in different replications. If I choose to have 5 nodes, it is like this. If I have to choose 6 nodes, like 6 stations, this is the most detailed model that I can have, and you see that there is quite overlapping with the real production rate. Okay, but it's important to say that I can tune the complexity of the digital tree. This is how the system learns. So this is the number of parts I'm producing. You see here the number of data, yes, I'm taking. And you see, after a learning of 10 parts, my estimate of production rate is very far from the real one. Why? Because I used only 10 parts for the learning or the generation. After 100 parts, I'm quite close until I'm here. This is for the production rate. This is for the system time. This is for discovering the buffer capacity. Okay, so to discover the buffer capacity, I need 1,000 parts in this case, to be sure. And this is to discover the distribution, the processing time distribution. We apply to a real case, so a real line, producing stators for motors for electric vehicles. We apply not to all this, to the old system, but only the system with the parallel machines here, and also a recirculation of parts, not so easy. And this is the model generated by process mining. And this is with our tuning model. So you see that the system is quite overlapping to the system. And we are able to discover after production of 5,000 parts, a few days, okay? And it took 30 seconds to discover automatically this model with all the parameters. Let me check the time because I have to control myself. Okay, so maybe I was quite fast, but I've given the idea of what we are doing in automated generation of digital twins. So our claim, okay, is that we want to be able in some years to support companies to generate automatically discrete event simulation models only using data. Obviously, let me add something. If I have a prior knowledge of my system, I can customize this optimization problem. And so I will be faster in the discovery. If I know that one station is important, I add a constraint here. If I know the buffer capacity, I will be faster, okay? So all the prior knowledge can be embedded in the math programming model. But our claim is to arrive to an algorithm that is able to generate complex simulation models. Now let's move to the other activity that is what I call online validation. This is more recent because automated generation of digital twins, the first PhD student defended the thesis last November. Okay, online validation and synchronization we started 1 year and a half, let's say. Now, I said that traditional validation is difficult to apply in online validation. Why? Because generally most of them are based on statistical techniques, or they are subjective. So they need an expert to observe the data, okay? And, you know, I cannot do this online in a system that is changing a lot. You know, we talk about reconfigurable manufacturing systems. You can have several reconfigurations, and you have to change the model, and then you have to validate the model. And also we have the fact that when you get the data are autocorrelated. And then applying statistical techniques with autocorrelated data is not easy. Then you need to batch data. And so you need more data. Okay. And it might happen that you need so many data that in the meantime, the system changed again. Imagine the semiconductor, a semiconductor facility. So they are, I can say that they are appropriate for offline and long-term decisions, and for systems that are static. Let's say they don't change frequently. Okay. Here you see, you know, the main references in literature on validation of simulation. So the Balch paper and the Sargent paper from two different communities. Online validation can work, must work with a limited set of data, and they should also validate not on the average. For instance, most of the techniques, they validate the simulation model by comparing the average production rate of the month or of the week from digital with physical, okay? But a digital twin that has to coordinate synchronized resources, it might be interested to the function, not only the average, the whole function, all the shape. For instance, these are two different functions that on the average are the same value. They have the same value, but they are very different. What if I have to coordinate the inventory levels with the production phase? I don't care the average. I need to synchronize processes. So I have to validate the function, not only the average. So what are we developing? Are we developing a method, let's call this way, that takes data from the manufacturing system, like these are data 14765, a sequence of data that are important, maybe the number of parts produced, for instance, in the period. From the digital model of the same system, I simulate, and then I derive a second sequence, and then I have to compare these two sequences. So it's not a comparison now anymore on the average, but it becomes a comparison of sequences. And so we studied the techniques that compare sequences, and you find this mainly in genetic, like a comparison between two DNA sequences. Now, you have a lot of algorithms to compare long sequences, and this algorithm has the goal to detect the distance between two sequences. So distance between trajectories. So we are developing a methodology like this, in which using algorithms like this, so sequence comparison algorithms, we can use this algorithm to compare KPIs at high level of the system, or more local KPI like the WIP in a certain area, the utilization of some stations, or I can also use to compare all the events of the system. I compare all the events in my simulation model, all the events in my physical system, and then I can have a validation indicator or not. These are the data logs that we are considering, like inter-departure time, system time, buffer level, and all the events. we need to validate both the logic of the simulation model, so the structure of the graph, and both the input distributions of my simulation model. And these are the procedures. Now, I don't enter into the details, but we have two kinds of validation. And I showed to you some numerical case in which we have this system with 5 stations or 5 machines. These are the processing time distributions. They are all finite buffer capacity. We have a 15 pallets recirculating here. We have one inner loop and one larger loop. Okay. So this is our indicator. On the x-axis, we have the number of parts. So how many parts in the sequence I'm considering. Okay. And this is the blue line is when the simulation model is perfectly aligned with my physical system. So I have a perfect simulation model. So I already know that it's valid. Okay. And you see that with several experiments, these are confidence intervals. I see that even with a few parts, my validator indicator is quite high. And the more data I get, the higher is until it's stable. Okay, so we are expecting this. And then we consider the same system, but with a simulation model that has a different mean in the processing times and different standard deviation. So it's not valid. And you see that this indicator is lower and stabilizes here. If the simulation model has a big bias in the input distribution, then this indicator is still decreasing. Okay, and you see, obviously, I need to decide that threshold, but after I decide that threshold, then I can say it's valid or not. This is what using the dynamic time warping algorithm. This is using another algorithm and the logic validation. This is the same system that is correct. This is if I use 12 pallets instead of 15 or 7 pallets instead of 15. And you see that indicators are lower, and the higher the number of parts I'm observing, the lower is the indicator. We compared also with simple statistical techniques like a pairwise test. And you see that after 50 parts, the pairwise test, the pair t-test, sorry, cannot decide because it doesn't have enough data. It can decide, it is not rejecting the assumption with 500, with a 5,000 is better, but we can decide that if it is valid or not, even with a few parts. You don't have any statistical assurance, I know, but you can apply online. Here I show to you our physical system. We are working in order to develop research in digital twinning. We need to have a physical system, or otherwise the research is really limited to theory. And if you want to convince a company, an industry, that you are doing research that can help them, you need to show real things that are working. And since I cannot allow an automotive manufacturing line in my lab, would be too expensive. So in our lab, we develop a physical systems using Lego technology. You know the Lego bricks? No? This is a 2-machine line closed system with Lego bricks. We have also much more complex systems in which here in red you see the parts. This is a buffer. These are the conveyors. This is a buffer with finite capacity. You have a sensors. We developed a control system. We have an IoT control system that the company helped us to realize. So this can be considered a physical system controlled with a digital twin. So with this kind of systems, our students are developing all the algorithms for digital twin operation, and they can really apply on a physical system. And you see here that by applying this, in the first part, the model is valid. The indicator is not below the threshold. Then it starts to go below, but then this can be a noise. But then something changed because there was a failure in this machine. And then the model was not correct anymore. So it was considered invalid. Let me check the time, it's fine. Now, we have two conference papers, one of some years ago, but then we stopped because we needed more experiments. Now we just submitted a paper to winter simulation, and we are working on the journal paper on this kind of online validation. And then let's move to synchronization. I know that in your department, you are also working on this. And I will show to you two different synchronization purposes, just the results. One is synchronization for alignment. So first I observe the real system, and then I synchronize the system in the past. This can be for, understanding what happened in the last 10 minutes. And you see that the real system is in black. And then the digital twin synchronized is in red. And then this is, in the x-axis, I have the time log, so in minutes. In the y-axis, I have the system time. So every time a part leaves the system, I record the system time in minutes, measured in seconds. And these are real experiments with our Lego factory system, okay? So the red one is done with this system. And then I synchronize the physical system. And then you see synchronization algorithms are working quite well, okay? Because, for instance, I don't have a complete information of the system. For instance, where the parts are in my system, I don't know, because I don't have a complete sensor technology. And so I had to make some biases, some guesses, but they are working quite well. So we can say that the digital twin synchronized every 5 minutes. So we are synchronizing every 5 minutes. It is quite well reproducing the real system. And then we have what I call synchronization for prediction. When I make a prediction can be very time expensive and also very cost expensive. Because I don't know, imagine I have to simulate all the shop floor for scheduling purposes. Or I have to simulate a semiconductor facility. Facility can be 2 hours of simulation. So let's assume that the synchronization has a cost. Okay, and these are all the reasons for a cost. Then we are trying to optimize the total cost for a synchronization. For instance, if I synchronize always every minute, then I have a complete information. My predictions updated every minute will be very accurate, but this will have a cost. So until now, we are working on a toy example, in which we have a planning horizon of n period, 10 times, for instance. At each period, I need to synchronize or not. So this is my action. U is equal to 1 if I synchronize, or 0 if I don't synchronize. But every time I synchronize, I pay a cost to CH. This is the synchronization action cost. At each time period, I want to predict how many parts I will produce until n. So the cumulative number of parts at period 10. Assume that the probability to produce a product is P. It's a Bernoulli experiment. So every period there is a Bernoulli experiment. So the synchronization cost, as I said, is CH, that is this one. And then at each period, I make a prediction, but this prediction will have a bias because my prediction will be y, let's say y hat, sorry, y bar here, should be y hat anyway. And this is the real expected value of yn, what I want to produce, given all these, okay? And h is a function, can be, I don't know, the square or the difference between the true expectation and my prediction, okay? So let's assume this is the bias cost. And so we need to decide each action to synchronize or not at each period. And we want this action to be optimal, looking at the minimization of the total cost function, that is partially synchronization cost and partially the bias cost. It's a compromise, it's a trade-off. Let's go here. For instance, we can have state-independent policies. So at period 3, I synchronize once here. At period 7, I synchronize. So I make two synchronizations independently on the realizations. So this is what I call a state-independent policy. If I look at the realizations at each period, my policy will be state-dependent, so much more calm. Okay, let's focus now at the right side. From top to bottom, I'm increasing the synchronization cost. So if the synchronization cost is very, very cheap, I synchronize every period, you see, honestly. If I increase the synchronization cost, then I start to decrease the synchronizations, and you see they are equally spaced. I'm increasing again until I have one synchronization on. And generally they are in the middle, but this depends on the process. With this with P equal to 0.5. Here you see the total cost for state independent. So I don't observe the state, so I make an independent state decision. If I also know the state, I decrease the cost. These are the average total cost as a function of the synchronization cost. If I would have perfect information, this is the lower bound. I can never reach this. But you see, state dependent is not so bad. Last, this is the average total cost on the y-axis, and the average number of synchronizations in bars, you see here, as a function of P, the Bernoulli parameter. So in the beginning and in the end, I almost sure I will not produce parts, probability P is or close to 0, or I'm pretty confident that every time period I will produce parts. So variability is very low. And you see that the average cost is low, and you don't need to synchronize. We know that the variability of this process is maximum when P is equal to 0.5. And you see for high variable system, you need more synchronizations. So this is what we derive from this study. So the number of synchronizations, let's say the synchronization strategy will depend on the variability of the production system. And so we need algorithms to decide for this. I will conclude saying that we definitely need new theory and tools for what I call operation of automated and autonomous digital twins. In my talk, I focused only on discrete event models. Okay, so everything related to simulation of tools, heating, and so on. Now they're not part of this frame. As far as the discovery, automated discovery, we have a graph to discover, but I can deal with the graph complexity constraints. I can define local constraints depending with the prior knowledge of the system. So I can really speed up my algorithms. There is always a compromise between model completeness, so a large graph, and parameter estimation. For instance, maybe the more is complex the graph, the simulation model, the more the parameters I need to estimate. And, you know, I think there will be a trade-off between this. The idea is to have put different constraints and to generate automatically 10, 20 different simulation models with different fidelities just by tuning my constraints. And then we have to focus more on more complex policies, so obviously. Online validation and synchronization, we are just, let's say, it's just starting, okay? But in these fields, I think there will be a lot of work. I conclude with this slide. These are my conclusions. I'm here, I'm available for questions, and I hope you enjoy my talk. Hope I was not so late. Yes.
Yeah, thank you so much, Professor Matta, for the insightful talk using the digital twin concept in the manufacturing systems and with the optimization models and the theory hidden behind the engineering field. Thanks. So, ladies and gentlemen, if you have any questions, please post in the Q&A channel or chat box. So we got one question here. Thank you, Professor Andrea Matta, for sharing. This is Wennan from our department, MSc Hong Kong U. I wonder if there are some cases where we cannot achieve real-time monitoring and management. On the one hand, there is a certain degree of delay in implementing real-time monitoring and management. And on the other hand, the calculation of OR will take a long time when we solve a large scale problem. Do you have any good suggestions for not being able to achieve real-time management due to latency and computing inferences, or whether we need to be concerned about these inaccurate times? Thanks a lot.
Yeah. So thanks for the question that it's really targeting some crucial points. So obviously, when you control a system, the time delay is important, you know. But there is, I think, a vast set of theories and algorithms to take into account the time delays. Okay, so the answer, okay. And then it depends on how let's say, the dynamics, how the system is really dynamic, turbulent or not. Okay, so for instance, semiconductor system, that is the most terrible system you might control, you might want to control because it's very complex. Okay, and also is also changing the dynamics. Your control is changing the dynamics, and so that would be very difficult. Okay, but surely you can always find systems in which you don't have these problems, but these problems will arise sooner or later. But we have a vast set of methods to manage these. But this comes from more from control theory than manufacturing field. Okay, so I think we should use this if we want to automate it. Okay. Mm-hmm. As far as the time for providing a prescription, then yes, you are right, because I didn't show an experiment. We had a paper in which we do the rescheduling of a production system. Our production system is still a Lego system, okay? And Lego system can be very fast, you know, because you have these small pieces that move. So imagine, so we needed to decide the optimal new dispatching in 5 seconds. Okay. If you want the real optimal solution, the optimum, now we are not able. So my team was not able to produce the optimal one. Okay. So for this reason, we need simulation optimization algorithms. We need to really work on simulation optimization algorithms, okay? And really we need, sorry, I come from 1 week of, last week I was COVID infected.
Please take care.
No, and talking 1 hour, it hurts. And for this reason, I'm working on different models. So sometimes in order to have an efficient simulation optimization algorithm, you can have a very first rough solution using very rough simulation models and then refine. Anyway, if you want the optimum, with the true optimum, so our theory to find the true optimum in real time, I think cannot be used. So you need heuristics, you need rough simulation models very fast, and we need really simulation optimization techniques.
Okay, thank you so much for the responses. The more questions that are coming. So next question is from David. Nice talk, Professor Matta. This is David from Hong Kong U. I wonder if you have any research ideas on digital twins on healthcare. Many thanks.
Yes, sure you have the hospital bed management. You need to decide the beds to accept or not a patient, and you have the risk that if you accept a patient that is not serious, then you have an emergency and then you can accept this. And so you have also, so you have to simulate why you need this bed occupied or not. You have the operating theater, so the surgical rooms. You have the emergency patient flow. You have many parts of the hospitals that would need, yes.
Mm-hmm.
And I think, when you talk about Hospital 4.0, there are some projects, at least here in Europe, I don't know in Hong Kong. You always have a digital twin. It's not a digital twin very detailed like the one we use in manufacturing, obviously. But there are concepts on this.
Yes.
I know, for instance, I know simulation models generated from data. This Professor C, yes, from France, that generated patient flows in the France country. And so they simulated different policies. But the model is generated only from data.
Professor Xie, right, from
Professor Xie.
Xie. Yeah. Okay, yeah, thank you so much. I think a hospital like 4.0 is very much like the industry 4.0 for the next generation smart manufacturing systems. Yeah, David also raised another question about the cost. One more question about the cost. Would the digital twins be so expensive that only big corporations can afford? Well, it's hard for researchers at the university to do real implementations.
As I showed to you, real implementations, like in this slide, I found only 21 implementations. Not a full implementation, but only 21. Okay, it was in the beginning. Yeah, only 21. Okay. So for instance, I never see in manufacturing a digital twin like the one that I explained. No, I never see. I've seen digital twin. What they call digital twin is just a monitoring. You are just one directional flow, not bi-directional. Okay. But you have examples of digital twins in also complex systems. For instance, all the chemical plants you have these big plants, very, very highly expensive, or power plants. They have a kind of digital twin in which they get from sensors and many variables, and then they have a control. Okay, but you know, these plants are really expensive, so you can afford the digital twin deploy. Okay, now the problem is how manufacturing companies can afford this cost. Okay, there are several tiers. Okay, first of all, you have big German companies, for instance, that are providing in clouds their data in order to allow the development of digital twins from their data. There are projects like this. Okay, so they are developing technologies in order to make easier and cheaper the digital twin development, because then they can use the results. And then I'm sure there will be actors, industrial actors, that we are developing, and we develop an IoT for smart algorithms. Because if from data you are able to generate a simulation model for free, then I think there will be companies just providing synchronization algorithm services, validation services. There will be a market like this. But David is right, now cost is very high. I see another question from Metaverse.
Yes, next question is from Chenling Yu. It's also from Hong Kong U. The question is, are metaverse and the digital twins very similar things? What's the difference between them? Do you have any thoughts, Professor Matta?
I think that, so let's see, according to my concept of digital twin, you must have a bidirectional flow. Okay, so the metaverse should prescribe me something to me, should have an impact to me. If I only stay in my digital environment, I think it's not a digital twin. For instance, generally I use, you know, the smartwatches. Many of you use the smartwatches that say, come on, you have to walk 100 steps more this hour, right? You sleep bad, you sleep well. Imagine this smartwatch, okay, that we use, a lot of us use. It is recommending to me to go to do gym, to do some walking every hour, okay? So it is something that is taking data from me, from myself, and then it's predicting the total number of steps I will do during the day, and then it's saying, come on, Andrea, now let's walk a little bit. This is a concept of digital twin, because it is prescribing to me an action. Then it's not fully automated, because I can decide I don't care. Okay, but it's a concept of digital twin. So the metaverse, if it is affecting my decisions, then it can be a digital twin.
Okay, thank you for the sharing. Another question is from the chat channel. Thank you, Professor Matta, a very wonderful presentation. D1 Run from Technical University of Berlin. I have a simple question. What's the key difference between model identification and the digital twins? Because I have read many papers on digital twin, but they are actually dealing with the model identification and model update. Thank you so much.
So can you, it's saying the difference between model and?
model identification and the digital twins.
Okay. Model identification.
Yes.
Okay. You know, model identification is, there are similarities, okay, because it comes from control theory, in which you have to control a system, and then first you identify the model, and then you control, okay? And if you come from production, from manufacturing, then the model is developed in a different way, using discrete coding to discrete event simulation model. Okay, so the purpose is the same, the techniques are different, and I think there will be a convergence on this. Okay, for instance, the model identification, they are using what they call, let's say, an analytical model. It's a kind of regression in which they estimate parameters. This is model identification. I assume a shape, for instance, and then I feed the parameters based on my data. Okay, and this is a kind of model. If you code in Rockwell Arena, this is another model. The purpose is the same.
Okay, thank you. Due to the time limitation, I may ask the last question on behalf of, like young researchers. We would like to target in your journal, for example, as the editor-in-chief. Can you give us some, suggestions? What's your journal looking for? And for some favorable topics, for example, and what's the future of your journal, so that the interested colleagues and the student can submit, some topics related to your future journal future directions. Thank you.
Perfect. I expected a question like this, so I have a few slides. If I want, I can.
Yes, please. Yeah.
Yeah. Okay. So, what I can say is that Flexible Services Manufacturing Journal, first of all, for the young researchers, is an interdisciplinary journal. Okay. So we attract people from management science, industrial engineering, operations research, mainly, other disciplines, but less common. Okay. But all they are oriented to improve services and manufacturing systems. So this is the first target. I say also to the young researchers to not focus a lot on this term flexible. Okay. This term flexible comes from the old name of the journal, that was International Journal of Flexible Manufacturing Systems, that then changed into this name. And unfortunately, we cannot change the name, because Springer is saying that every time a journal changes the name, then the impact factor decreases, because researchers cannot understand what is doing the journal. So we have the heritage of the term flexible, but please don't be discouraged if your paper is not flexible. Okay, because it is an old-fashioned, okay, an old-fashioned term, okay. And, it's like a naval research logistics journal. It's not talking anymore of naval applications, right?
Yeah.
It's logistics, okay? And we have to keep it flexible. So don't be discouraged if your paper is not flexible. First thing, but very important. Okay. It was founded by Katrin Stecke. The young scholars, they don't know Katrin Stecke. I think some of you, yes. And then George Shantikumar, I think George, I think very well. And then moved to Ansoto Gunther, a German professor. that was teaching in South Korea some years ago, and then moved to me. These are the main areas. Okay. And so you find healthcare, you find services and manufacturing, but since healthcare had a very important role in this journal, it is attracting quite a good number of papers, then we dedicated a focused area on healthcare. And then we have traditional areas, transportation and logistics, operations and supply chain management, and scheduling. Here you find the area. Okay. Now, I believe that everything related, the future will be data. Models now should not be models that I build offline, should be models that I build as far as I increase the knowledge of the system. So, but since the models in the future will become data dependent, then we need to consider the uncertainty also of the data, because the uncertainty of the data will transfer on the uncertainty also. I will have a model uncertainty, and this will have an impact on the decision. So anyway, independently from the application, I think that this trend of building models, not just from observation, but data-driven models, and to make decisions based on these data-driven models, okay, then I will be very important. It's now important and more and more. What I don't suggest is to what we receive often. I build a model with machine learning in Python. I compare 3 different machine learning algorithms. I put in the paper, and then I submit the paper. Okay. Here, what is the innovation, the originality? It's just that you have taken few algorithms, implemented, coded, compared, but there is no additional knowledge. Okay. So I'm trying to not to incentive, let's say, this kind of papers. Okay. But really something that is adding knowledge. Okay. And here you see some main figures. Okay. The impact factor, that is always important. And here you see in the last 4 years, I did yesterday this, the number of final decisions for publishing, rejected, desk rejected. So we have more or less something related from 10 to 15% of acceptance rate. Okay. Our journal has 4 issues, so we have a kind of 34 slots per year. So we need to select the right papers because the number of slots is limited. So many desk rejections are done, even if the paper is reasonable, but each paper, if we dedicate a slot to a paper, this paper should have a value. Okay, should be distinguished from all the other ones. And so sometimes we are forced to reject it very fast, even if, you know, this paper can be published in other journals, but because we have a number of limited slots, and I don't think it's important to increase. Just to make you understanding the idea of the journal, this is what I ask to reviewers, okay, when they judge a paper. Obviously, if they are familiar with the topic or not, if the merit of the manuscript is excellent, above average, and so on, okay? But these 2 things are important, okay? I ask to the reviewers if the research problem addressed in the manuscript fit with the real needs from companies. So we don't accept only papers that are good theoretically, but also that make a value in real organization. Okay. So, for instance, if a paper is not aggressive, so the assumptions are very far from reality, even if the math is quite good, we don't accept. So this is very important. And then we ask, and this is, I introduced very recently this question. I asked the reviewers if they learned something from the review, from that paper.
Okay.
So I can understand how the paper is. For instance, many times the reviewers say, no, I did not learn anything from this review. And so why should we accept? Okay. So really a paper should have a value, a potential value. If we found the paper as a potential value, I ask reviewers to help the others to make explicit this value that is still potential, but not very clear. And then obviously there are papers that in which reviewers learn a lot. Now, some key selling points. First of all, I think we are a small journal, but with a quite high reputation, because we are in the first quartile. We have more than 30 years of history. And this journal is not related to any association like IIE, IEEE, POMS. Is independent from applications and surviving without having any association behind is not easy. Okay, because you know associations help. We have a short response times. If the paper doesn't have a potential value, we recommend desk reject, so the author is not waiting. And then also we protect our reviewers that are quite good, but we don't want overload them. It is a double-blind review process since 2-3 years. And then I succeeded to convince Springer to finally implement the data and code sharing policy. So I think this will be, I think, the first journal on production systems that starting from July, will ask authors mandatory to share data and code. And this, I'm sure, will help a lot the community. We'll ask to share data and code at least with a minor revision. So we don't ask immediately. If the paper is going well in the peer review process, then we ask data and code. And then other reviewers can use the same data, can reproduce the same experiments, the comparisons, benchmarks will be easy. And this will be implemented in a few months. I think that it is very important to assign the good reviewers for a paper. And the good review process starts from associate editor. If I assign to an associate editor that is not very, let's say, expert on a field, then the peer review process will be bad. By experience, I can tell. So if we receive a paper that has a value, but I don't have in my editorial board the right expertise, I ask to an expert in the field. I appoint as a guest editor. Okay, he will manage only that paper and stop. But the peer review will go. So I can guarantee that the papers will be reviewed by experts in the field. Because I cannot have 200 associate editors in the journal. Okay. There are 1 or 2 special issues per year. Ray, you know this.
Yes, thank you so
one of
much
the
for your support
editors.
for running the
Yeah.
special issue this year.
Yeah. And we apply what I call ethical policies. For instance, it's my pity that after I became editor-in-chief, I chose to never submit papers in this journal. It's not a Springer rule, it's my rule. So I don't submit my papers. When components of members of the editorial board submit a paper, I manage in a special way in order that there are no conflict of interest. But because of this, I had to publish on different journals. But my editorial board, yes, they can publish. But this is just to increase the confidence in our journal that is small, but is managing the paper in a very quite good way from ethical point of view. We are trying to help the community by sharing data and code. And we try all the best, even appointing guest editors just for one paper. And for young researchers, we have once per year. Now the deadline is already gone, but I show to you this video. The dates that you see are old, so you have to think 2 years more, okay? But we dedicate an award for young researchers.
Sorry, Professor Matta, is there any songs? Yeah, we
Sorry?
cannot hear.
You cannot hear?
Yeah.
Okay, it's just the music, don't worry.
Okay.
It's just music. So it's not the spring 2021, will be 2023. And will be December 2023. So we dedicated an award for young author, and there will be a prize not of money, but the agreement is the young student can receive a certain amount of money in Springer books. That I think for young researchers is better to give not money, but books for publishing more papers later. Yeah. And so this is what we started for the young scholars. And so I really stimulate the young students to submit papers for the next call.
Okay, thank you so much, Professor Matta. I think a younger, researchers or students, they will be interested, submit their excellent work to your journal. And thank you for offering these opportunities for the young generation of academic in the near future.
You're welcome.
So due to the time limitation, I will briefly, share. The next speaker is Professor Su. Is the advisory editor. Is TRE. So we are looking forward to see you guys again. Now it's very late in Asia areas, but thank you so much, participants. We still have over 100 guys. Okay, staying with us.
Thank you, because for you it's late. So.
So finally, I will invite my colleague, Dr. Yong-Hong Kwok, to give some closing remarks. Dr. Kwok, please.
Yeah, thank you, Ray. And of course, so thank you so much, Professor Andrea Matta. So it's very happy. I'm very happy to see you here. Yeah, so every time I attend your talks, and then I learned a lot. I still remember you work a lot of on different things, simulation, optimal control, and then also in manufacturing and healthcare. And then now you are working on digital twin. I'm very happy to see a lot of these exciting applications, not just in research, but you also put it in practice. I mean, so I'm very happy to see them. And I hope that next time we don't need like now, I mean, we don't need digital twin or metaverse, but you come physically to Hong Kong, and then to visit us. And then so we will show you around Hong Kong, not the virtual world.
Yeah, it will be a pleasure. It will be a pleasure. So let's hope maybe end of the year.
Yeah. Thank you.
Route to Singapore. Why not?
Yeah, thank you.
Yeah, hopefully we can see you.
Thank you again. Wow.
Yeah.
Yeah. Okay, thank you so much, Dr. Kwok, and thanks again, Professor Matta. So, ladies and gentlemen, this is the end of this talk. Thanks a lot.